Hello, good afternoon. I'm going to be talking to you a little bit about Greenwaves technologies and next generation of a processor that we're doing based on RISC-V called GAP9. I'll try and be quick because I know that there's a happy hour at 5:30, so I know I've got a really hard stop at that time. Greenwaves, just to give you a little bit of background on Greenwaves and also a bit of background on our first generation processor so that you understand which markets we're going after, and then I can go more into depth on GAP9. So we're a French fabless semiconductor startup. We sell chips. We're based out of Grenoble in France, founded in 2014. And we're really focused on one specific market, which is bringing advanced machine learning and signal processing into edge devices that run on battery power or energy harvesting. So our observation or our wish is to bring these kind of functionalities into devices which are really power constrained, rather than the normal edge devices that one thinks of. These are wearable devices, devices which have a lot of difficulty getting power to them, or it's very expensive to get power to them, or there's no power at all. And this can be used in a variety of different spaces. I would say that wearable is something that we've actually stumbled onto. Like most startups, we had a certain vision, and we've enhanced that vision over time. But these are some of the areas where we're seeing interest in bringing these kind of AI functionalities, particularly in the workspace management kind of area. Counting people in offices and things like this, and also, as I said, wearables, but also a wide range of other applications. To solve the problem of actually bringing AI and signal processing to these kind of devices, we feel that there's some really fundamental things that we have to do in the process design that we're producing. The first thing is that we have to be able to bring these kind of advanced AI capabilities down to something which has an MCU class energy consumption. And the way that we approach this problem is parallelization, architecture extensions, so ISA extensions, which RISC-V helps us enormously with, and something that which we call explicit memory management, which I'll cover a little bit later. The second thing that we feel is a very important attribute of the things that we're bringing is agility, which is the ability for the SoC to actually change power state extremely fast. So we're not wasting time and wasting energy as we move between different processing states. So we heavily use dynamic voltage and frequency switching inside the chip. And we bring in all of the power control into the chip so that we can switch very fast between these states. The final point, which is a point that we feel is very, very important as well, is programmability. And this is for a few reasons. Most of the real-world applications that we look at, particularly in the audio space or vibration space, are not just about neural network acceleration. They're about signal processing as well. And secondly, the neural network, anyway, the machine learning sphere is moving so fast that every single month there's a new paper that kind of changes the state of the art. And we want to be experts in accelerating things which are happening today, not the things that happened last year. And then finally, an important point that we think that we bring, and this again is aided by RISC-V, is to have a single code model across the entire SoC. So all of the cores that we have in the SoC are actually identical, which means that anywhere where we run, when we compile code, we compile it once and it can run anywhere in the chip. So our first generation product was called GAP8, still exists, and is now actually shipping in production. So we've shipped first production orders on this. It's based on 5 years of research in a program called PULP, which comes out of ETH Zurich and University of Bologna. It's a product that has a very advanced architecture, but in a process which is fairly mature, 55 nanometer low power from TSMC. It has 9 extended ISA RISC-V cores in it, which are organized with 1 controller core and a 5-core cluster. The compute cluster allows it to actually do these algorithms in an extremely efficient way by allowing us to reduce clock frequency and hence reduce core voltage, which gives us a quadratic benefit there. We've been shipping it in HDKs since May 2018, and as I said, we're now shipping production quantities. GAP8's already achieved some pretty interesting and impressive performance figures. Here are just two examples of that. A QVGA Face ID, which we've now launched open source. This is a full stack which goes from the face detection through to the face re-identification based on a SqueezeNet CNN. And that's delivering 1 milliwatt per frame per second on face detection and 22 milliwatts per frame per second on the actual identification network. That's giving you the ability to embed things like owner detection or change of person detection into battery-operated products which are sitting on really the edge of the network. The second area which I'm illustrating there is infrared people detection. So that's an infrared photo taken from a small, low-power infrared sensor, 80 by 80 sensor. Very low power, 40 milliwatts. You can take a picture in about 100 milliseconds. And then we can do image pre-processing and human detection. So we box those humans that are seen at a meeting room table and distinguish them between them and hot chairs or cups of coffee or whatever it might be. That, again, allows you to bring facilities, occupancy detection, and people counting in building management systems in a device that can last on a AA battery for 5 years. So that gives you an idea of GAP8 and what we're doing with GAP8, and now I want to talk a little bit about our next generation. So GAP8 kind of combined a market-leading architecture, parallel cluster, but with quite a mature semiconductor process. GAP9, we've tuned this architecture with experience that we've gained from the customers using and developing products around GAP8, and we're exploiting a market-leading semiconductor process, which is GF22FDX. We believe it will establish a new capability power consumption point in the industry, with being able to cope with problems which are up to 10 times larger than GAP8, at up to 5 times less power than GAP8. So some of the power consumption figures that we've already published for GAP8, you can divide them by up to 5 times. And it increases both the agility and programmability dimensions that I described before. So what are some of the things that we've evolved in the architecture? The first thing is being able to cope with larger problems. In the ML space, coping with larger problems means more memory, but it also means using that memory in a more effective way. So we've tripled the internal RAM. We've worked a lot on improving the bandwidth inside the cluster and also inside the memory system in the SoC. We've also added a hardware compression unit, which can actually compress the weights that are in a neural network, and also in signal processing scenarios can actually compress inter-layer signals, doing both bit packing and bit unpacking on the fly inside the DMAs. We've added more compute states, so the cluster top frequency has moved up to 400 megahertz from 175. We've got a new power state. One of the things we found was that in a lot of situations, we want to wake up extremely fast and then start configuring some I/O or some peripherals to start taking in data before we actually get to maybe a pre-processing state, even before, that's way before the inference state itself. So there we've actually integrated in an LDO that allows us to have a very low power state where we're around about 1 milliwatt, but we can get to that power state in a few microseconds, whereas previously in GAP8, it took us about 600 to 700 microseconds to wait for the DC-DC to stabilize and to get to the first instruction executed. Finally, more flexibility. GAP9 integrates a trans-precision floating point unit. So we have floating point support, which we did not have in GAP8. The floating point support covers 32-bit floats, 16-bit floats in IEEE format, but also BF floats in 16-bit format. So that's the type of float which has the same range as a 32-bit float at the expense of a reduced precision. And then what we could call a BF float 8, which is the same as an IEEE 16-bit float in terms of range, but very little precision. There we're talking about 1 sign bit and a couple of bits of precision. That sounds very little, but it's extremely interesting to have this state where you can do a calculation, keep the accuracy in terms of the range, the precision during the calculation, and then trim down, just keep the range at the end of the calculation. We've added new bidirectional digital audio interfaces, an additional CSI2 camera interface, and also hardware encryption on the fly, and a programmable unclonable function block. Giving you an example of the kind of performance you expect from GAP9. This is on a benchmark on a mobile net V1 CNN, and it's in comparison with an STM32H7, so an M7 core from ARM. This is showing the ARM can do an inference on that network in 162 milliseconds, and that's achieving a frame rate of 6.2. And it does that with 65 million cycles. On GAP9, we can do the same operation at 4.77 million cycles, which means we can reduce our clock speed down to 29 megahertz, at which point we're consuming an active power of 5 milliwatts compared with 170, which is a 34 times power reduction there. If you move GAP9's clock up to its maximum speed, then we go 14 times faster. And you can also use that headroom that you've got to actually tune the algorithm. MobileNet has the ability to tune the algorithm to gain accuracy by using a larger image or reducing this channel scaling knob on the algorithm. If we do that, we go to about the same frames per second, divide the power by 3, and deliver double the accuracy. But architecture is 50% of the story, if that. Tools are the rest. We find lots of different types of customer that are coming to us. Some people are expecting a packaged solution. They really want something that just works out of the box. Some people want, MobileNet working end-to-end. They want to tune that a bit, but they don't really want to get into the implementation of it. And some people, they want to revolutionize the world. They've got their own filtering algorithm or something like that, or a new convolutional layer or something of that sort. And they actually want the tools to be able to optimize that on our architecture. So we have people who want solutions, people who want prepackaged fine-tunable networks. We have people who want really expert tools to exploit the architecture. And we have a number of tools there. I can't talk about them all here. If you're interested, please come to our stand. We're on the Open Hardware Group stand in the exhibition hall. One of those areas of tools is the whole tools which allow us to go from neural networks all the way to the architecture. Here we take a tools-based approach, i.e. we don't want to give a developer a big black box that they have to press a button, and if it works, great, but if it falls over, they have absolutely no idea what went wrong. So we take an approach of delivering specific tools in this, and one of those tools is a tool that we call the autotiler. The autotiler is a tool for explicit memory management. This means that we actually exploit the fact that we know what we need to move in terms of memory at the point where we push the compile button. Your image size is not going to change. Your CNN input size to a convolution layer is not going to change. Your weights are not going to change. Even in the audio domain with time-based signals, you've still got things where you have known size at compile time. So instead of using data caches in the architecture, which would be extremely inefficient on these kind of stream workloads, we actually pre-compute all of the memory movements for the DMAs in the architecture at the point of compile time. So the autotiler is actually a code generation tool. It allows us to generate code which does all of those memory movements and also does all of the calling of a kernel function inside our compute cluster without the programmer having to worry about writing those. And that's an important step, because for a programmer, that's a really hugely complex problem. The programmer, at an algorithmic level, just has to write their kernel function, parallelize it, vectorize it, and assume that all of their data is actually in the L1 memory close to the core. Then they write a model of how they want the data moved around and divided up with constraints. And then we finally constrain the autotiler with how much memory we're going to give this algorithm, and then the autotiler produces and writes code for that to occur. The autotiler also allows us to describe a model, an entire graph of assembled kernels. And we provide a number of already written kernels for things like all of the neural network layers you're likely to come across, fear filters, FFTs, signal processing stuff as well. And these can all be assembled together, and then you've got another problem, which is what do I do with the intermediary values? How do I bring in the weights into to layers which require parameters? And all of that is handled by the autotiler again. It produces code and tries to optimize the movement of everything around the hierarchy so that we don't transfer stuff more than once, if possible, into the cluster. At the next layer, we have a tool called NNTool, which does model extraction from TensorFlow, from TensorFlow Lite, graphs, and also does post-training quantization. And then at the top level, we have a model library with a number of different models that we have already written for GAP8, things like all the mobile net varieties, including the V3, the recent V3 one. And there we have also scripts for doing quantization, which is training aware. This describes the autotiler in a little bit more detail. Basically, this is our memory hierarchy. So you have an external L3 RAM flash, which may be on a hyperbus or an octospy or something of that sort. Then we have an L2 memory area, which is the main SOC memory. And then we have a shared L1 memory area, which is shared between all of our processor cores. So basically what the autotiler is doing is generating all the code to program the two DMAs that you can see there, one which is responsible for moving things between the L3 and L2, and one which is responsible for moving things between the L2 and the L1. And it's generating all the code necessary to triple buffer, double buffer, et cetera. And as I said, you can constrain it with different memory configurations, which becomes very, very interesting if you want to start loading more than one algorithm on there. So maybe you want a signal processing algorithm for audio stream, plus a CNN, plus another CNN for an image stream. So GAP9 development boards are available in early 2020 for lead customers. The GAP9 Simulator, we have a full simulation program that's inside our SDK, which is an open source SDK available on GitHub. And that simulator allows you to do a 20% error, cycle accurate simulation of the chip. It also gives you wave diagrams so that you can see exactly what's going on inside the chip, signals in either hardware signals, so core activity, IPC, et cetera, or OS activity, or even application activity. And that's been in customer hands in its GAP9 version since May 2019. GAP8 is now shipping in production, as I said. GAP8 development boards and evaluation boards are actually available directly from us. We have a couple of boards, one for vision applications, one for IR applications, and we're continuing to expand those out. As I said, GAP SDK are available on our GitHub repository, and please do come and visit us on the Open Hardware Group booth if you have supplemental questions. It's difficult to go into the detail that's necessary on this in a 20-minute time period, and especially when all of you want to go and have a beer. Are there any questions? All of that code is written in C. So essentially, the kernel functions are written in C, the models are written in C, and those are, apart from the autotiler itself, the library, we release all of those generators inside our SDK. So you can actually see that code, and you can actually modify directly that code. So you can see the implementations of every single kernel we've done. So if you want to modify the actual kernel, that's totally possible to do, or add a supplemental kernel generator in, that's also possible to do. What we try to do is make it very visible all the way down to the base system. And actually, the architecture is relatively easy to program compared with other architectures which are on the market for accelerating neural networks. So it's you know, a shared memory model. It's very, very transparent. The package size of the GAP8 is in an AQFN package. It's 7 by 7. In the GAP9, we're expecting to ship it in both a BGA package and also in potentially wafer in a wafer level CSP package as well. It depends on customer feedback that we're getting actually at the moment from the lead customers that have GAP9 in their hands. Okay, the extensions are in, I'm at 0 now, so you're losing your beer time. But the extensions that we've added are in really 3 areas. One is DSP type instructions, so zero cycle loops, saturation clipping operations, max, and so on. Then we have a number of SIMD extensions in 8-bit and 16-bit. So we have dot products, various different operations on vectors. Vector adds and dot products with accumulation into 32 bits, for example. So we can do a 2-4-way 8-bit vector dot product in a single cycle with an accumulation into 32 bits. And then we have a bit shuffler in every core. So we can do pop count, we can do bit extraction, bit shuffling. They're not, these were extensions we've developed over the past, well, the project has been running for 5 years. So these were the standardization extensions. So in the standard instructions, we have IMC, and in GAP9, we have IMCF, RV32.